Welcome. In previous class, I have discussed on the chemical shift values, and I also give some data that we have to remember the chemical shift values for some data like if the carbon that is attached to 1 degree carbohydrates, and if the hydrogen attached to 2 degree carbohydrates and 3 degree carbohydrates, what are uh, the chemical shift values? Let's say this case if it is 1 degree carbohydrates, then for this H, that chemical shift value is 0.9 ppm, and similarly if it is this is 1 degree and if it is 2 degree, then that is going to be 1.3 ppm, and if it is 3 degree, that hydrogen atom is that is 1.7 ppm. So that things I have discussed in the previous class. I also discussed on aldehyde, ketones, and carboxylic groups that hydrogen have what the chemical shift value is. Okay, so today I'm going to start the topic that is factors affect the chemical shift. Factors affecting the chemical shift. What are the factors that affect the chemical shift? Okay, so first factor is electronegativity. That I have seen that if let's say if that carbons, and if it is 1 degree, and let's say this is the carbons, or we can say let's say CH3 CH2, here that Cl is there that we have discussed, and since this is 2 degree carbohydrates, so 2 degree carbohydrates, for that chemical shift value is 1.3 ppm. Okay, now if you attach this carbon with any electronegativity groups, then what happens that this has the tendency to do minus I effect. So this will take electron from it means that here that electron density will be reduced. It means this will affect the chemical shift values. So we have seen that due to chlorine, how much that increment will be, that we have discussed that for chlorine that increment value is 2 ppm. So this the chemical shift value for this hydrogen atoms, let's say CH3 Cl. So for this hydrogen atoms, the chemical shift value will be 1.3 plus this 2. Okay, so total is going to be 3.3 ppm. Okay, so if the electronegativity groups are present near to any 1 degree, 2 degree, 3 degree, or any atoms, then that will affect the chemical shift values. That is, we have to add this how much increment it will do. Okay? So that is the one factors, that is factor chemical shift is affected by electronegativity. And next factor is very important, that is anisotropic effect. Okay, so this anisotropic effects that while discussing on whenever I give you some chemical shift value that we have to remember. So on that time I told that let's say for that this values, what I said that if the group is, let's say any double bonds is there, where that hydrogens is there, on that case its chemical shift value is going to increase, that is 4.5 to 6.5 ppm. Also I told that whenever this is C triple bond C and here H is there, and its chemical shift values is going to be 2 ppm. Okay, and I also say that if the group is, let's say, aldehyde group, for this the chemical shift value will be, that is 9 to 11 ppm. So this amount of chemical shift means high chemical shift value we see 9 to 11 ppm. And whenever it is, let's say, acid groups, for this hydrogen the chemical shift value is 11 to 12 ppm. See, the chemical shift is very high. So what is the reasons behind this high chemical shift value? Why for this chemical shift value is very high? Although for, let's say, if it is 1 degree, let's say this, for this chemical shift value is 0.9 ppm. So why this chemical shift for some molecules it is very high. So hydrogen it is very high chemical shift, and for some cases it is very low. So see that for alkyne its chemical shift is 2.2 ppm, whereas for alkene its chemical shift is 4.5 to 6.5 ppm. Also that benzene rings, I have told that for benzene rings for this hydrogen the chemical shift value is 6.5 to 8.5 ppm. So why this chemical shift value is very high? So that is explained by the help of anisotropic effect. So the high chemical shift value for this protons is the because of the anisotropic effect. Okay, so how this anisotropic effects, due to this the chemical shift value of this proton is very high, that we want to look. For that, first we will look that for benzene rings, first we look that anisotropic effect for this, and first for, let's say, for aromatic rings, aromatic systems. Then we look for that anti-aromatic systems. Then we will look for non-aromatic systems. Okay, so this anisotropic effect, due to this effect the chemical shift values are very high. That why the chemical shift values, that protons of this aromatic systems is very high, that is explained by anisotropic effect. On that we will study in three categories. One is aromatic system, another anti-aromatic systems, another is for non-aromatic systems. Now if it is aromatic systems, let's say first is aromatic systems. So first we know that what is the conditions for aromatic systems, that we very well know that that should be a planar. Planar means sp2 hybridized, and there should be have a conjugations. Yes, that these are that there should be a conjugations, means that alternative pi bond should be there, that must be there. So that is the basic things for any system to be aromatic, like it should be a planar and it should be a conjugations. Okay, and that should follow Huckel rule. Huckel rule. What the Huckel rule says, that for aromatics, that for n plus 2 pi electrons, where n is equal to non negative integers, means that n can be 0, 1, 2, 3, 4, 5, etc. So if these conditions any system follow, then that are arithmetic systems. So let's say if we have then benzene rings. For this benzene rings, what we have, how many here, that how many so here if you apply this Huckel rule, then this is 4n plus 2 pi. So how many pi electrons are there? How many? That is 1, 2, 3, 4, 5, 6, 6. So here if you solve it, then how much we will get? 4n plus 2. 6, then 4n plus pi electron, that is pi electrons are 6. So this, then this will going to be 4n, that is equal to this going to be 4. So n is equal to 1. Okay. So n is follows from this. So this is a pi electron systems. Okay, so this is the theoretically way that we can say that these systems are arithmetic and these systems are anti-arithmetic. But for the shortcut, what you remember, so we no need to look always all these things. We only remember that count the pi bonds. So here 3 pi bonds. Whenever number of pi bonds, not pi electron, number of pi bonds is equal to odd, then these are always arithmetic. So we should not yes, obviously that it has to be a planar, it has to be conjugation and should follow Huckel rules, but we will not use always these formulas. We simply say that if it is follows this rule, like it should be a planar and it should have a conjugations, after that we will only look that number of pi bonds. If number of pi bonds are odd, then that is arithmetic, and if number of pi bonds are even, that is anti-arithmetic, that is not a arithmetic system. So only follow count the number of pi bonds. Here 3, 1, 2, 3. So 3 number of pi bonds and 3 is odd. So this is arithmetic systems. Okay. So in this way we can easily say that which system is arithmetic and which systems are anti-arithmetics. Now we will look at how that anisotropic effects affect to this pi arithmetics affect to this arithmetic systems. We will talk on this benzene ring. Okay. This is a benzene rings. Okay, now what is there? So in this benzene rings, it has a pi ring currents. It has a pi ring current, so you can easily say that in arithmetic systems, it has pi ring current of arithmetic ring, which generates induced magnetic field and magnetic field in the opposite directions of applied magnetic field. So for aromatic systems, that pi ring currents generates a induced magnetic field in the opposite directions of the applied magnetic field. So this effect is called the anisotropic effect in pi ring systems. This effect is called anisotropic effect of the aromatic systems. So what it means that, let's say it is the benzene rings. Let's say the benzene rings, and it has these pi systems, and it generates its own pi ring system, pi ring currents, and due to this it produces a magnetic field. Okay, so its magnetic field is, let's say, like this. Okay, it produces a magnetic field due to the pi ring currents, and now here we are giving a magnetic fields, applied magnetic fields. We are applying to these directions. Okay, now what happened that what we see that in aromatic systems, this firing current of aromatic ring will generate an induced magnetic field in the opposite directions of the magnetic field. Okay, so here that magnetic field, here the applied, this is the applied magnetic field, applied magnetic field. So this is the applied magnetic field, and that this firing current generates an induced magnetic field which is opposite to the applied magnetic fields. It means that due to this it generates, this firing current will be in this directions. Okay, sorry. Firing currents are in these directions. So firing currents are just opposite to the applied magnetic field. So here that induced magnetic field is in these directions, this direction, and these are going this direction. So that applied induced magnetic field is in these directions. So what we see that this the applied magnetic field and the induced magnetic field, these are opposite to each others. Okay, but now whenever it is going to here, then in these times this is the same directions. So what we see here that if you draw a cone here, let's say inside this cone, and here also if you draw a cone here, sorry, this is the wrong structure. That benzene ring should not be this structure. I'll draw this. that benzene rings would be in this. Okay, this one, and it generates an induced magnetic field like these directions. Okay, and now you are giving that applying magnetic field, let's say B naught, and this is applied to these directions. Let's say here, this is the B naughts, and that induced magnetic field by these aromatic systems is this is in these directions. Okay, so what we see here, that this is these directions, and here also that due to that aromatic ring, that induced magnetic field also these directions. This is the B induced, this is Bi. Okay, so now if you draw the cone here, the cone will be in this direction, the another cone downward also, cone is also for these directions, and you are applying that magnetic field here, B naught. This is the applied magnetic field. Okay, so now in the aromatic systems, what you say, that induced magnetic field is just opposite to the applied magnetic field, and that is whatever there in the inner side of the cone. Okay, and this outer side of the cones, let's say whenever this side, this is the outer and this is the outer sides, in this B naught, this and this getting the same directions, this and this getting the same directions, but inside the cone, this and this getting the opposite directions. It means that that B effective that the B effective is B naught for this uh, for inside this, this is the cone, for inside cone, or we can say inner area, we can say here that B effective is where B naught and inside the cone, these are in the opposite direction, so B naught minus Bi. It means, let's say if you are applying that B naughts, that is let's say 5T, and induced is let's say 2T, then this is going to be 3T. It means that B effective is decreases. Okay, B effective which decreases in this case. Now that outside the cone, here I write that outside the cone, or that also called that outer protons. Here that B effective is here that B effective, B induced and B naught, B naught and B induced, that is induced magnetic field, are in the same directions. It means here B naught plus Bi. It means here B effective is increases, and we know that B effective is directly proportional to the chemical shift. It means that B effective is high, then chemical shift is also high. It means what we say that outer protons have high chemical shift, whereas the inner protons, means inside the cones, inner protons have low chemical shift. Okay, so for aromatic systems, what we see that uh, whatever that protons, that is outer proton, means outside the cones, they have that high chemical shift. And interestingly, what is found that whenever you're seeing that aromatic benzene rings, all these protons, these protons and these protons, these protons and these protons, and these protons and these protons, all are outside the this cone, means that all these protons have that high chemical shift. Okay, because this all the protons of a benzene rings are outside the cones. So all the protons are outside the cones, then all have the high chemical shift. That's why we see that for aromatic systems or for a benzene ring, we see that the chemical shift value, chemical shift for benzene ring, we see that that is 6.5 to 8.5 ppm. Okay, because all these protons are outside the cone. Previously, I have drawn the aromatic systems in this way, and where that I drawn that this way, this, and the cones are I drawn like this, which says that one proton is inside that cone. So this is the wrong structure. Actually, what experimentally found that the benzene ring is exist in this manner, and all the protons are outside the rings, and we get that all the protons, that chemical shift is in this range 6.5 to 8.5 ppm. Okay, this is the for aromatic systems. Next we look for anti-aromatic systems. So here what we see that for aromatic systems, outer protons, proton means which are outside the cones, they have high chemical shift, and inner protons have the low chemical shift. Okay. This is for the aromatic systems. Now we will move to that anti-aromatic systems and non-aromatic system. After that we will solve some examples. Okay. So next I will move to the anti-aromatic systems. First I will discuss on that what the Huckel rule says. What the Huckel rule, what it says that it should be planar, and that means sp2 hybridized, and it should have the conjugations, alternative conjugations. That means that should have the conjugations, means alternate that double bond should be there, and it should be cyclic. It should be cyclic. There also I have forgotten to written. It should be cyclic. Okay. After that, what the Huckel rule says, if these conditions are satisfied, then the Huckel rule says that for anti-aromatics, this is 4n. for n pi electrons. It should satisfy the for n pi electrons where n is non-negative integers, that means 0, 1, 2, 3 dot dot dot, but that should not be negative values like negative 2, negative 3. This should not be, it should be the positive integers. Okay, so if it's satisfied, then that is a anti-arithmetic systems. Let's say we have that compounds like this compounds. So here what you see that for n pi electrons. Okay, so here that how many pi electrons are there? 1, 2, 3, 4. That is 4. Okay, it has 4. Now this 4n equal to 4, so this n has to be 1. So this is the anti-arithmetic systems. Okay, or the shortcut is that we always remember. Shortcut is, if it satisfies these three conditions, then just count that number of pi bonds. The number of pi bonds is 2 and 2 is odd, so this is always anti-arithmetic. Okay, so always for arithmetic, number of pi bond, not pi electron, number of pi bond is odd, then this is arithmetic. And for anti-arithmetics, number of pi bonds is even. Note that this is number of pi bond, not number of pi electrons. Okay, number of pi bond is odd, then that is arithmetic, and number of pi bond is even, then that is anti-arithmetic. So this is the shortcut you have to remember. That should be satisfy these conditions. Okay, this condition first it should satisfy. After that, apply this trick, then we easily say that which is arithmetic and which are anti-arithmetics. Now what you see that for anti-arithmetic systems, let's say these molecules. Okay, here that the pi electrons, it has that pi ring coherence. Here that B naught applied magnetic fields, and this will be in the same directions of the applied magnetic field. It means whenever this is coming, okay, so this and this will be in the same directions. Here that this direction it is coming. Just opposite to that arithmetic systems here. Okay, so now if you draw the cone here, okay, so what you see that this B naught, let's say this is the B naught. So for inside the cone, or we can say that inner protons, that B effective is equal to in the same directions. So B naught plus B induced. Okay, this is the B induced. So B naught and B induced in the same directions. So for inner protons, B effective increases, whereas for if I go for the outside the cones, for outside the cone, outside the cone, or you can say outer protons. So this and this now become the opposite directions. It means that B effective is B naught minus B induced. It means here that B effective is decreases, but here that B effective increases, and we know that B effective is directly proportional to chemical shift. So from here I says that for outside the protons, for inner protons, for inner protons have high chemical shift, and for outer protons have low chemical shift. Okay, so this is the just opposite of the aromatic systems. For aromatic system, what you see that for inner protons they have the low chemical shift. Inner protons have the low chemical shift, but for anti-aromatic systems, the inner protons have the high chemical shift. Okay, so if I write code for aromatics systems and here for anti-aromatic systems, here that inner protons are low chemical shift, whereas for that anti-aromatic systems, inner protons have high chemical shift. And next is outer protons. Here they have that high chemical shift, but for this anti-aromatic systems, outer protons have low chemical shift. So you just remember for aromatic systems, and this anti-aromatic system is just opposite of what the aromatic systems. Okay, anti-aromatic system is just opposite of aromatic system. So this is the effect of anisotropic effects for aromatic and anti-aromatic. So if I define that for anti-aromatic systems, what is the anisotropic effect? We say that anisotropic that anti-aromatic systems generates a pi electron rings which is in the same directions of applied magnetic field. Okay, unlike that aromatic systems where that pi electron ring is opposite directions of the applied magnetic field, but for anti-aromatic system with the same directions of induced magnetic field is same directions of applied magnetic field. Okay, that's why these and these are getting the opposite each other. Now next we'll discuss on non-aromatic systems. Stage non-aromatic systems. So we see that for non-aromatic systems, it not follow the Huckel rules. Okay, so it not follow the Huckel rule. Okay, and it not follow the Huckel rule means that it is not planar. Okay, it means that it has sp3 hybridized carbon atoms. unlike that aromatic and non-aromatic system that has to be a planar, it means that is sp2 hybridized. But it is for non-aromatic system, it is not planar, means it has some anti-aromatic, some sp3 hybridized carbon atoms. Okay, and it not follow the Huckel rule. Okay, so for this, what actually non-aromatic system, we just say that not follow the aromatic rules, not follow the Huckel rule, that are called non-aromatic systems. So for this, what is looked at, this is the similar case of aromatic systems. Let's say this type of groups. Okay, now if we give that any acid groups, then what will happen, that it will attack, this pi bond will attack here, then it will becomes let's say this type of groups. So now this becomes same as this, and since this is attacked, so here become positive charge and here come the one hydrogen, two hydrogen. Okay, here everywhere the one hydrogen is there. Here that positive charge H came. Okay, so it means that this is the sp3, this is the sp3 center carbon, so this not follow the Huckel rule. Now that this is the same, whenever you look that here that it is same as that aromatic system. Here the number of pi bonds are 3. 3 means odd number of pi bonds. So it is similar to like aromatic systems. So it is follows the same anisotropic effect as the aromatic system. It means that this pi electron ring that produce an induced magnetic field, this which is opposite to the applied magnetic field, just the same as the aromatic systems. Okay, so here that, and what this will becomes, I'll just say this, since this is sp3 hybridized carbon atoms, sorry, not this is not the sp3, this is so this become the sp3, sorry, this become the sp3 hybridized atoms. Okay, so since this is these all are planar and this is not in the planar because this is sp3 hybridized, so this is change its structure and it becomes and which is this is not in the planar, so that will going to be like this. Okay, and that comes here and this becomes something like this. Okay, this is then positive charge, so whatever that atoms are there. Okay, here that one hydrogen here and one hydrogen is here, so which is not in the planar system like this sp3 hybridized carbon atoms, that will go in a unplanar, so this go far away, so this is sp3 hybridized and all the remain as like aromatic systems, so 1 2 3. Okay, so this is just like aromatic systems. Now whenever anisotropic effect, how we apply that, if we apply that B induced, then this ring generates an induced magnetic field which is just opposite of the applied magnetic field, means this is this direction, just like aromatic systems. So here also what you see that outer protons have high chemical shift and inner protons have low chemical shift. This is the same as aromatic systems. Okay, because you see that this is the same as that 3,5 bond, this aromatic, and whichever that not in planar, that will go away. Okay, and all this remain as aromatic system, so it will follow the same rule as aromatic system, that due to that pi electron ring induced magnetic field which generates, that is opposite to the applied magnetic field. Okay, so now here that this protons is there. Okay, now if you draw that cone, then this cone will be like this directions, and another will be like this direction. So these protons, this, let's say A, and let's say this B, so these protons will be inside the cones, so that we can inner protons, and it has a low chemical shift value. So whenever you compare that chemical shift, then this HA will have the low chemical shift, and HB has the high chemical shift than HA. Okay, because this is inside the cone. Okay, and it follows that same as the aromatic systems. Okay, so this is the all about of aromatics, anti-aromatics, and non-aromatic systems, how that anisotropic effect apply to this these systems. Okay, so now we also seen that we have also seen that anti-aromatic, so this anisotropic effect, that is applied to alkene systems, this alkene systems, and this is also applied to this alkyne systems, and this is also applied to the aldehyde systems. Also this anisotropic effect also applied to this acidic protons. So these all have high chemical shift, and that is explained by anisotropic effect. How? Let's say if it is a alkene systems, okay, and it has, let's say here hydrogen atom is there, here also hydrogen is there, alkene systems. Now you are giving that B applied magnetic field, then it will due to this pi, what it will generates a induced magnetic field. Let's say this induced magnetic field will like this. This way it may generate an induced magnetic field, and this is the same way it will be the opposites to the applied magnetic field. It means this directions. Okay, so here we will draw a cone, and here also we will draw a cone. Okay. Now you see that this applied magnetic fields and this B induced, this is the B induced, are just opposite to each other. So here we also see that whenever you calculate that B effective, then we say that B induced, this is in these directions, and these are the opposite directions of it, means they will cancel. Okay, so it means that B effective is decreases. So if the protons are present of these systems inside the cones, then they will, the B effective value will be decreases, and B effective is directly proportional to chemical shift. It means that inside the cones, if protons are present, they have the very low chemical shift, and we see that this is going to be these directions, and outside the cone this B induced and this going to be the same directions. It means that this is for inner protons, or inside the cone. Okay, for outer protons we see that this and this getting the same directions. Okay, whenever this going to this and this directions, this B induced, sorry, B applied magnetic field and this is going to the same direction. So for outer protons we see that B effective equal to B applied plus B induced. It means that B effective is increases here. B effective increases. It means chemical shift value is increases for the outer protons. And what we see that in that alkene system, this all the protons are outside the cones. That's why for alkene system we see that these protons have that high chemical shift values that lies nearly that is 4.5 to 6.5 ppm. Okay, because these all are outside the cone, means these are the outer protons. Okay, and they have that high chemical shift value because their B effective is adding with the applied magnetic field. Whatever you are giving that applied magnetic field and this B induced, they get added it, so that this B effective will increases and the overall the chemical shift values increases. Okay, that is the reasons for alkene systems we see that chemical shift is 4.5 to 6.5 ppm. And for alkyne systems, let's say this is the alkyne systems, let's say here is the hydrogens, here is the hydrogens. Okay, now here you are applying that B induced, then here also we can say that this and this, okay, so here that B induced is in these directions, and let's say that this alkane system also that induced magnetic field will in these directions. Okay, so if you draw the cones here, then we see that this B applied and B induced are opposite inside the cones and these protons are outside the cones, so this should be the high chemical shift value, so that we should get that high chemical shift value, but for that alkyne system we get that 2 ppm. The reason is here that we say that these alkyne systems, that this is not just experimentally what it is found that these alkyne systems, whenever you will give B induced to any systems, then wherever you are giving that alkyne system, that will rotate, that alkyne systems will rotate. Okay, so here you are giving that B induced, then it will rotate like this, here will H will come. Okay, the rotations will occur. Experimentally found that wherever you are giving B induced, that H will come to that directions. Now if you draw that magnetic field, induced magnetic field, this will in these directions. Okay, so now here if you draw the cone here, let's say this is going to these directions. Now if you draw cone here, sorry, so this will going to be, it is going to be like this. Experimentally it is found, whatever we found experimentally, that we will study in a theoretical. Okay, so first is experiment is important. So experimentally, what is found that wherever you give me that B naught, that is applied magnetic field, that will orientate to in this directions. It will not orientate like this directions. So here you are giving B effective means H will come to this directions. Okay. So that will orientations will happen. So that experimentally what is found that whenever you give me applied magnetic field, H will be in the same directions. So this it will come to this directions. Now that this magnetic field, induced magnetic field will be this directions. Okay, now if you draw the cone here, that these hydrogens will be lies inside the cones. Okay, and this B effective here for this is B not, because this is the same direction, so that will be cancel it up. That will get subtracted. It means that B effective H decreases. That's why here we see that low chemical shift. That is 2 ppm. Okay, for that, for alkyne systems, that protons are outside the cones. That's why we see that chemical shift as 4.5 to 6.5 ppm. So this is all explained by the anisotropic effect. Okay, now we will solve some examples. After that we will wind up the class. Okay, so let's the first example is this system. Now compare the chemical shift values. Compare chemical shift. So for this case, so this is aromatic system. So this is the aromatic system. So for aromatic systems, what we seen that this will be the this directions, this applied magnetic fields, induced magnetic field, this directions. Okay, so that and you are giving that V naught is in this directions. So if you draw the cone here, the cone will be like this, and the cone will be like this. Okay, and note that one point here. Note that for alkyne systems, this protons, alkene systems, this protons has chemical shift 4.5 to 6.5. Okay, but this is in alkene systems. Let's say C, double bond of C, and here we have one is CH2, another we have that H. This case, this is that uh, vinylic protons, and this is the allelic protons. Okay, and this anisotropic effect is applicable only to this vinylic protons only. For this, that chemical shift is 4.5 to 6.5 ppm, but this is not applicable. This anisotropic, this anisotropic effect is not applied to allelic systems. These protons, that chemical shift is not equal to 4.5 to 6.5 ppm. Okay, because this anisotropic effect is applicable only for the vinylic protons, not for that allelic protons. If allelic protons is there, its chemical shift value will be, this is the 2 degree, so this is 1.3 ppm, so this proton has 1.3 ppm. Okay, 1.3 ppm. After that this carbon is there, then for that some will be applied, but this allylic proton, this anisotropic effect is not applicable. This is applicable only for that vinylic protons only. Okay, we'll solve these questions. So here if you compare that chemical shift values, then what, this is inside the cone, so inside for aromatic system, if it is inside the cones, then that will have very low chemical shift value. So chemical shift value very low is C. Okay, after that what you look that see here that these protons, this proton is the benzylic proton, so sorry, this proton is directly attached to benzene rings, so these protons, this anisotropic effect will applicable. Okay, but this proton, that anisotropic effect is not applicable, only to this. Okay, so after that HD is, D will be the highest, okay, because this is directly attached to benzene ring, so here that anisotropic effect is applicable, that is this proton has the 6.5 to 8.5 ppm. Okay, but this is not directly attached to benzene ring, so these protons, that chemical shift is not equal to 6.5 to 8.5 ppm. Okay, because this is not attached directly benzene ring, so which proton directly attached to benzene ring, there this anisotropic effect is applicable. So this is highest because here anisotropic effect is applicable, and that is going to be 6.5 to 8.5 ppm. Okay, after that this is that benzylic, so benzylic will be the after this directly attached to benzene ring, this after that this is that benzylic proton, then this will come. Okay, then this is A, then we will have that B. So this is the order of chemical shift. And next we will go to that 18 aniline systems. So here we see that these are the inner protons. Okay, so what we see that first we will look at whether it is aromatic or non-aromatic. Okay, so for aromatic, what we say that should be a cyclic systems, and that should be sp hybridized, and conjugation should be there. So all the conditions are satisfied here. After that we will count that number of pi bonds. If it is odd, then that is aromatic, and if it is even, then that is anti-aromatic. Okay, so count 1 2 3 4 5 6 7 8 and 9. So number of pi bond, that is equal to odd, that is 9, so this is aromatic. So for aromatic, what we have seen, inner protons have low chemical shift, and that outer protons have high chemical shift. It means that chemical shift values of this all inner protons have that low chemical shift, and this all that outer proton has the high chemical shift. So first outer protons, then inner protons. Okay, this is for the analysis. So first we will see that whether it is anti-aromatic system or aromatic system. If it is anti-aromatic system, then first inner protons, then outer protons. Okay, next questions. Here we look that compare the chemical shift of the given aromatic compounds. Okay, for this type of questions, what we have to look that we will count that electron pi electron electron density. Okay, so first we will say that this is aromatic or not. So here that all the conditions of aromatic system is followed, that is it is all are sp2, and this is cyclic, and conjugation is there, so this is all satisfied. Now we will apply that whether number of pi bonds we will count. So this is 1, so 5 bonds is 1, so this is odd, so this is aromatic. Okay, for this case also this is 1 2 3, pi bond 3, so odd, so this is also aromatic. Okay, for this also pi bond 1 2, here also this is also in conjugation, so this is also 2 electrons, so this is just like a pi, so this is also pi bond is 3, so this is odd, so this is also aromatic. Okay, now all are aromatic. Now how will you compare that chemical shift values? So for this case we will calculate that electron density. So electron density is equal to what? That count that number of pi that is, it says here 1 2 3, here the number of pi electrons upon number of protons, that is the things. Okay, here we will calculate the number of pi electrons, after that number of pi bonds. The number of pi electrons is how many? That is 1. Okay, pi bond is 1, so pi electron will be 2, because 1 pi bond carries 2 electrons, so this is 2, and number of proton is 1 2 3, that is 2 upon 3. Okay, here is 2 upon 3, and for this case, so electron density will be number of pi electron, so 1 2 3, 3 bonds, so one pi bond carry 2 electrons, so this will be 6 pi electrons. After that number of protons 1 2 3 4 5 6, 6, that is going to be 1. Okay, here electron density is first number of pi electrons, sorry, pi electron, that is 1 2 3, so that is going to be 6, and this is 1 2 3 4, this is 4. Here also one hydrogen will be there. Okay, so 4, that is going to be 5, 6 upon 5. Okay, so now if you calculate here, this is going to be 1, and this is going to be 1 point some values, 1.6 upon 5, that is 5 1 ja 5, and then so 1.2, and this is going to be 2 upon 3, this is going to be 0 point some value, let's say 0.9 approximate. So here we see that pi electron density for this case is high, and then this, and we know that electron density is indirectly proportional to the chemical shift. It means that electron density order is first is C, then we have B, then we have A, then chemical shift order will be just opposite, that will be A, then B, then C. Okay, this is the answer. Why? Because electron density is just opposite of the chemical shift. Okay, so note that electron density is number of pi electron, not number of pi bonds, number of pi electrons upon number of protons. Okay, first number of pi electrons, then number of protons, not number of protons after the number of pi electrons, first number of pi electron upon number of protons, that is equal to electron density, and electron density is opposite of that, inversely proportional to chemical shift. Now in these questions, arrange the following in the increasing order of the chemical shift. Okay, so this is the different questions. So here we see that these all are anisotropic effect. So everybody that anisotropic, that range is 6.2 to 8.5 ppm. But now the question is here, this is the electron donating group, and we have seen that electron donating groups decreases the chemical shift. This we have seen that, and we have seen that electron donating group decreases chemical shift, and electron withdrawing group increases chemical shift. Okay, so for this case, For this case, compare the chemical shift. Then what have, this is the electron donating groups. The electron donating group that decrease the chemical shift. Okay, so this electron density will be, if the electron density will be there, if it come, then this will come to this ortho, and this para positions it will come. And we see that if you apply here plane of symmetry, then this E, then this is also become E, and this is D, then this is also become D. So electron density is coming to this ortho and para. Okay? And experimentally found that here ortho will get the high electrons because this is nearer also. So what you say that electron density order will be passed ortho, after that para, then these meta electrons are not coming, then meta, then chemical shift value will be just opposite of that. That means first will come meta, then we have that para, then we have that ortho. Okay, and now the for this hydrogens, whatever this hydrogens, for this case, since this electron donating group, so this will be this value will be the lowest. Okay, so density will be lowest will be this. Let's say this is let's say we give the name here. Let's say this is A, and let's say this is B, and let's say C, and then let's say this is D. Then A will be the lowest, and this C will be the highest. After that ortho, that is B. Then we have this D. So this is the chemical shift order. Okay. Similarly, now this case, in this example, this is the electron withdrawing groups. So electron withdrawing groups increase the chemical shift. It means that this will be the highest. Okay, this F will be highest, so that we will see that here also plane of symmetry is there. So now this will be A, then this will also A, this will also B, and this is C. Okay, so it will take electrons from ortho and para. So this will be that highly electron density will be decreases from here and here. So if decreases, then that value will become high. So after F, then A, then we will have that C, then we will have the B. Okay. Because here this is the electron withdrawing groups that increase the chemical shift value. Okay, because it will withdraw the electron. So here also electron density will decreases, here also it will decrease, here it will not go, so this will become the lowest. Similarly, for this case, this is that electron donating groups, this is also electron donating groups, and here we see that plane of symmetry is there. So this is A, then this is also become A, this is B, then this also become B. Okay, and here also that plane of symmetry is there. So this is C, then this is also C. So chemical shift order will be, so since this is electron donating groups, so this C will be the lowest. Okay, after that ortho will be the ortho and para. Ortho is A, after that para will be there, so para is not there, then we will have the D. Okay, this will be the chemical shift order. So this is the electron donating group, so this will be decreases, that's why this C will comes. After that it will comes, it will take from A. Okay, and para is not there, so this meta will come. Okay, this is the highest. Similarly, for these questions, this is the very important questions. Here what you see that So this is that electron withdrawing group. This is also electron withdrawing group. And here also you see that plane of symmetry is there, POS is present. So if this is A, then this is also A. If this is B, and here also plane of symmetry is there, it means this is also A. Okay, so these all are A. And this will be the B, and this will be the C. Okay, so now this is lies in the aromatic systems. So chemical shift value, of this aromatic system will be the high. First will be A, then we have that B, then we have that C. And now this problems for this, but you see that this will be the shift to here, and this will shift to here. It means that CH3 CH, here C, double bond CO minus H. Okay, so now here that electron density is decreases. It means this is the positive charge it becomes. So it means that first this haldehyde groups, this will be the highest. First D, chemical shift order. First D, after that this B, because here that chemical electron density is here positive charge has come, so this is decreases. Here also H is there. So first D, then we have that B. Okay, because this electron has gone, here positive charge has come, so after that B, then we have C, then we have that A. This is the chemical shift order. Okay, and the last questions. Here that chemical shift order will be, let's say these all are electron donating groups. Now we're comparing this HA, HB, HC and HT. For all the case, but you see that this is also electron donating groups, this is also electron donating group, this is also electron donating group, this is also electron donating group, and this is also electron donating group. Okay, now that electron donating groups, but this decreases the chemical shift. So where it decreases, so first we will discuss on that electron density. Electron density where will be the high, so which will give more electrons, this groups, this, because this is that this is going to give that pi electrons, and this is less electron activity compared to this, so D will be the highest. Then we have the C, then we have that B, then we have the A. That B, this C has high electron density than B, because here due to steric hindrance it will give less electron density compared to this. Okay, so this would be very clear that here that CH3, this is also electron donating group, but due to that steric hindrance this will give low electron density compared to this. Here no steric hindrance, that's why it will give that high electron density. That's why first will be D, then C, then B, then A. Okay, then that electron density is opposite to the chemical shift, so this chemical shift order will be the just opposite, first A, then B, then C, then D. This is the answers for these questions. So today, after this, next class we'll discuss more. Thank you.